Hello and welcome to another video of Dr. Webb, the Graduate Classical Mechanics series. Today we'll solve a concrete civil engineering problem, which is to find the shape of the tunnel that needs to be dug between New York City and Los Angeles to enable the transport of a gravity train between the two places. So the definition of a gravity train is you simply drop the train on tracks at New York City and it goes through the earth by the force of gravity alone and comes out at Los Angeles. There are some assumptions we're going to make along the way. I'll state them. So some of the points of interest is how close you get to the Earth's core, the total time it takes for this process, some obvious precautions that you need to take. And I gave away the answer. The answer turns out to be, the curve turns out to be a hypocycloid. So we'll also talk about the various properties of that curve. So if you'll notice, this is a spherical object. The Earth is a spherical object. And to minimize the transit time, we need the section to be through a great circle. So even a great circle is not in the coordinate system, which is the flat coordinate system. So the first thing we have to do is discover the Euler equation for polar coordinates. So let's do that. So in polar coordinate, the metric ds squared, which was dx squared plus dy squared, becomes dr squared plus r squared d theta squared. I believe I did some calculation like this in one of the earlier videos, and I won't bother doing it. I'll just ask you to accept this on faith. Now the curve that we want to find can either be found as r as a function of theta or theta as a function of r. We're going to assume that r is a function of theta. Then the term r prime will refer to dr by d theta. All right, so since we are favoring r, the proper thing to do is to take out the d theta outside. So when I write ds, I'm going to get the square root of dr squared plus r squared d theta squared. And now I'm going to take the d theta outside, which means that I get dr by d theta here plus r squared, and then I'll take the d theta outside. Dr by d theta is just r prime, so this is going to be the square root of r prime squared plus r squared d theta. So we have got our first thing, which is the line element. Now the time functional is the thing we have to extremize. So the time functional t will depend on the path gamma. Well, that is just the integral from 1 to 2 ds divided by the speed at any given time. We had a similar time functional for the brachistochrome problem. So if you've not seen the previous video, please see the previous video. So I'll write here GCM17 for the brachistochrome problem. This is a very similar problem to the brachistochrome problem, except the velocity of the object is not going to be given by square root of 2gy as it was in the previous problem. It's going to be slightly more complicated because gravity does change as you go inside the Earth. So this is the time functional, and if you vary this, the delta t should be equal to 0. So that's going to be the variation of 1 to 2 square root of r prime squared plus r squared d theta, that's your ds, over the velocity. Now, velocity can be found by energy conservation. So I'll do that off the side. The potential energy of the particle plus the kinetic energy never changes. So at New York City, I'll write Los Angeles over here. We are assuming that the train is just dropped, so the kinetic energy is 0 here. At any given time, there's going to be kinetic and potential. So some arbitrary point P inside is going to have kinetic and potential. Initially, kinetic is 0. The total energy will be called capital E. So by energy conservation between New York City and Los Angeles, I have the energy at New York City, which is the total energy E. And that total energy is purely potential. So that's the potential energy, which is also the total energy. And inside, it's going to be a combination of kinetic energy and potential energy. So it's K plus the potential energy V as a function of R. Therefore, the kinetic energy, which is 1/2 mv squared, is just going to be E minus V of R. And now I can solve for the velocity. So velocity is just going to be 2 over m E minus V of R. I'll just write it as E minus V, the square root. So that's going to be our velocity in the denominator. Okay, that variation should be equal to 0, which means our function f inside, which is a function of r prime and theta, is equal to the square root. Now I'm going to ignore 2 over m because the mass of the train doesn't change. So I'm going to simply ignore that. Just keep things that do change. So r prime squared plus r squared divided by E minus V of R. So that's going to be our function, which now at this point, I'm going to let you work things out, and you can show that the Euler equations work out exactly the way they did for Cartesian or generalized coordinates, and we can write our Euler equation as follows. It is d by d theta of del f over del r prime minus del f by del r equal to 0. So that's the Euler-Lagrange or Euler equation for this case. Now, last time we proved a corollary, and that is if f does not depend on theta, then we can conserve the so-called Jacobi integral. I refer you to the previous video for the proof of that corollary. Here also, you notice that theta never appears nowhere in this expression. So we can use the corollary here. So I'll write by corollary to Euler, the quantity r prime del f by del r prime minus f will be constant. So we have to determine the constant. How do we do that? In this problem, you can actually do this as follows. When the particle is at the bottom, so I'll draw another picture here. So here's our point 1, which is New York, and point 2, which is Los Angeles. Now the path between the two, I roughly know is going to look like that. It's a portion of what's called a hypocycloid. We'll prove that. So this, you notice that at the closest point, if we call this distance R0, the distance between the center of the Earth and the bottom of the tunnel, then the rate of change of r with respect to theta is 0. That's the property of a tangent. The tangent tells you, the horizontal tangent tells you that the rate of change of r with respect to theta is 0. Elsewhere, the tangent is making an angle, and here the angle is 90 degrees with respect to the r vector. Okay, so here's the r vector. So we're going to use dr by d theta equal to 0. Now, let's impose that condition. So if dr by d theta is 0, that means r prime is 0. That's r prime, because r prime is dr by d theta. So this part vanishes. So I'm going to get negative 0 minus f of f is a function of three things, r prime, and theta. So it's going to be a function of r naught, r prime is 0, and theta must be equal to a constant. And what is that equal to? If you put the value of f at for 0 at r prime, r naught, and e and v of r, I get negative square root of r naught squared. So square root of 0 squared plus r naught squared divided by the square root of e minus v of r naught. So that's our constant. We have determined the value of the constant, so it's just negative r naught over the square root of e minus. I'm going to call v of r naught v naught. It's a potential at the lowest point. Now we have determined the constant, and we can go back and look at the Euler equation, which is this again. Therefore, r prime del f by del r prime minus f is equal to negative r naught over the square root of e minus v naught. Now it's time for us to solve. The rate of change of f with respect to r prime, the numerator is the only thing that depends on r prime, the denominator does not, so I'm going to leave the denominator alone. So I'll write it as r prime times 1 over the root e minus v times the numerator. So that gives me half r prime squared plus r squared to the power negative 1/2. And then I go inside and differentiate the function. So I get 2r prime. So the half and the 2 cancel out, minus f itself. So that's going to be the whole thing. And all that is equal to the right-hand side, which is r naught over root e minus v naught. Now, if I don't write anything, then v is simply to be assumed as a function of r. Right now, it's a good idea to solve this entire problem for an arbitrary potential, because then you can work on any problem you can work on the shortest path or shortest time, also known as the brachistochrone, for any potential. Now, this is the advantage of Euler over the method of John Bernoulli. If you remember last video, I showed you how John Bernoulli had this tremendously clever idea of using Fermat's principle for light to solve the brachistochrone problem. Well, once you have the potential to be arbitrary, like this one, you can no longer use those cute tricks. So now it's just a matter of doing the technical work. So let's do that. So here I'll take the 1 over root e minus v outside, since it's common to both terms. And then I have r prime squared divided by the square root of and then here, because I've taken the 1 over e minus v outside, I just get r prime squared plus r squared. Okay, now for some simplification, I can take the common denominator here. So you'll notice that this factor of r prime squared cancels off. There is a negative sign on the left side and a negative sign on the right side. I'll cancel them like that. And now we have a rather beautiful looking equation. So let us try to write it out. Okay, so first of all, the square roots are there and you don't really want them. So I'm going to square both sides. If I square both sides, then the numerator now becomes r to the 4. Then I simply have e minus v times r prime squared plus r squared, and that's equal to r naught squared over e minus v naught. Let's just quickly check the units look good. You have an e minus v type term. Here you have r to the 4 divided by something like r squared. So that's effectively meter squared in the numerator. And here also you have meter squared in the numerator. So the units at least look good. Now lastly, let us solve for r prime squared plus r squared. So since I'm bringing it there, I'll take the e minus v naught upstairs. So this is our beautiful equation that we have to solve. Now, this is a general expression and it's valid for any potential. So I'll just mention that. So if you feel inspired, you can try different potentials and see what kind of curves you generate in your computer. That's just something for you to do. Right now, we have to figure out what the potential is inside the Earth. So that requires us to use Gauss's law for gravity. So here's a little interlude. How do we use Gauss's law for gravity? So let me first draw the Earth and a Gaussian surface inside the Earth. Because I want to find the potential at an arbitrary point inside the Earth, the spherically symmetric Gaussian surface I would use would look like that. It's got radius r. Now I know that the gravitational field is going to be pointing down. And I also have the convention for the outward normal vector, which is pointing outside. So the angle between G and dA is 180 degrees. Okay. All right. The full radius of the Earth is this one. I'll call it r sub e. So we are using Gauss's law. Okay. Gauss's law, if you recall, for gravity would be very similar to electricity. So let's first recall what Gauss's law for electricity is. The closed flux of E dot dA, something you learn in university physics. So that's going to be the enclosed charge divided by epsilon naught. Now, epsilon naught is very special to Coulomb's law. If you think about Coulomb's law is electric force equals K Q1 Q2 over R squared. Similarly, Newton's law of gravity is G Newton M1 M2 over R squared. So G Newton and K have the same status. This is Coulomb's law. And that's Newton's law of gravity. The reason I don't just pull out the actual Gauss's law directly is because I want to show you how to think when you're in a pinch. And I always remember Gauss's law for electricity because I teach that each time to university physics students. Gauss's law for gravity never comes up. So this is more natural to me. Now I'm going to show you how to recover this knowledge. The relationship between epsilon and k is the following. Epsilon is 1 over 4 pi k. So if you replace epsilon naught by 1 over 4 pi k, you're going to end up getting 4 pi k times Q enclosed. Well, K and G have the same status. So all you have to do is replace K by G, Q enclosed by mass enclosed, and E by G, and I'm done. I have now Gauss's law for gravity. So let me write Gauss's law for gravity now. Phi C G instead of E, which is the double integral over a closed Gaussian surface. That's Gaussian surface S. This is your S of G dot dA must be equal to 4 pi times Newton's gravitational constant times the enclosed mass, where the enclosed mass is the mass enclosed by the dotted orange surface. So by proportionality reasoning, we already know the enclosed mass, M enclosed, must be equal to the total mass of the Earth times R over RE cubed, because volume is proportional to radius cubed. And here we are assuming that Earth has a constant density. So right away, this does not apply to our real Earth. So right away, I tell you that I'm cheating. The Earth, as you know, is not constant density. It starts out with a crust where the density is something like that of aluminum and silica, like 2.7 grams per cc, and then it goes on to the mantle. Mantle is about the same density as the moon, which is one of the theories of how the moon was formed, was that very close to the Earth's initial formation, a Mars-sized impactor hit the Earth and produced the moon. And the material that would have been ejected at that time is most likely the density of the mantle. That's why the moon's density is about 3.3, which is the density of the mantle, grams per cc. And then after the mantle, there comes the other layers like the outer core and the inner core. So the Earth is certainly not constant density, but in this calculation, we're going to assume constant density. And so for the entire calculation, this entire calculation is fictional. If you were actually building a tunnel, you should take into account the variable density of the Earth. This calculation gets to be much more complicated. It can still be done. You can still use Gauss's law, because even if the Earth has layers of variable density, Gauss's law is still valid because spherical symmetry still exists, more or less. So that's the assumption we're making. Earth is a constant density in writing this mass enclosed. So let's work on the left-hand side of Gauss's law. I've already told you the angle between G and dA is 180 degrees. So I'm going to have negative G times 4 pi r squared. That's the left-hand side. And that's equal to 4 pi Gn mass enclosed. So we have our 4 pi's cancel out. And so we have our formula for G. As a vector, G would be negative G Newton M enclosed A R over R squared. Now M enclosed is that, so times the R vector R hat, sorry, forgot that my screen mugshot covers up some of the writing. So anyway, that's what you have. if you solve this equation and put vector signs everywhere. Now m enclosed is that, so I'll substitute it. This tells me that G equals negative G Newton, mass of the Earth, over R, because R squared cancels with R cubed. I'm left with a R in the numerator, and then RE cubed, R hat. So that is our formula for the gravity inside. Observe that it's a linear function of R. The gravity becomes 0 at R equals 0, which is to be expected because in the center you're getting equally tugged in all directions. But as you get closer and closer to the Earth, you actually feel lighter because this R value keeps decreasing. Your maximum weight occurs at the surface. So that's pretty interesting, and this has actually been verified by people when they go deep in a mine shaft. Some of the mine shafts that have been dug are several miles long, so you can actually measure the weight change with sensitive apparati. Now, what we need is the potential, not the gravitational field. So for potential, we need to integrate. So let's call this the initial point I, and that the final point F. So we're going to integrate from I to F. Okay, so the change in potential, delta V, is going to be the negative integral from I to F of G dot dr. This is exactly the same kind of integral you would do to find potential in any electrostatics problem. So that's your dr vector, and G is pointing inside. Once again, you have the 180-degree business. So delta V is V final, which is V at the surface minus V inside. And that's going to be negative integral I to F G times dr times cosine pi, or 180 degrees. Cosine pi and the negative sign cancels out, so I get V at the boundary minus V inside is equal to the integral from little r to capital R sub e. The negative sign is gone, and G, which is just the magnitude, is this part without the negative and the r hat. So I'll copy that down there. So I get Gn me r over re cubed dr. rdr, one of the simplest integrals in the world, is just r squared over 2. So let me write that. This is Gn me over 2 re cubed, r squared at the upper limit minus the lower limit. All right. Now, the potential, what's the potential at the surface? Now, the force at the surface is going to be Gn me times the mass, some other mass. Let's say you're standing there, over re squared. So the potential energy is defined, the potential is defined as the work done per unit mass. Okay, so when you, the relationship between the force and potential energy is F equals negative du by dr. So the potential energy can be found by this, so it's just negative Gn mem over re. That's the potential energy at the surface. The potential is the potential energy per unit mass. So you divide out by your mass. So the potential at the surface is just, what did I call it? I think I call it V naught. No, that's not V naught. It's V of Re. Sorry, V naught is the potential at the lowest point. Never mind. So the potential at the surface is just going to be negative Gn me over Re. So we have everything. That's V at Re. Let's substitute that, and carry on. So this part has to be done with great care because otherwise we will not be solving the right problem. That's why I'm taking my time with this. So I'll put this back in this equation, put this back in that equation. So I get negative Gn me over Re minus V as a function of R is equal to all this stuff. So I get, let me multiply it in. So I get Gn me over 2Re minus Gn me R squared over 2Re cubed. So observe that there is a GnMe over 2Re over here and GnMe over Re with a minus sign. When I bring it over here, it becomes 1 plus half, which is 3 halves. So I get V of R. That's the negative V of R. So if I bring the negative also to the right side, I will get negative 3 halves GnMe over Re. And then because I've canceled the negative signs, this just becomes positive. So finally, we have our answer. Let me write this in a slightly compressed fashion. So no negative. That's G sub n me common to both terms. There's a 2 that's common to both terms and a Re that's common to both terms. And then I have negative 3 plus R squared over Re squared. That's the great formula for the potential inside the Earth. The gravitational potential inside the Earth. It's a calculation you never had to do in elementary physics because there are very few problems that involve a tunnel being dug under the Earth. Now, one thing to quickly note is that the potential at the center, which is given by setting little r equal to 0, is actually 150% more than the potential at the surface. Because the potential at the surface is negative Gn me over Re, whereas at the middle of the Earth, it is negative 3 halves as much. So it's 150% more. That's just an interesting factoid. Now, to simplify our writing for the future, I'm going to introduce the following notation. I'm going to call eta the ratio between the location of the train at any given radial location of the train at any given time divided by the radius of the Earth. So by construction, eta will always be less than or equal to 1. The equality will be achieved at Los Angeles and New York City, and it will be less than 1 throughout the journey. Also, I'm going to introduce a notation eta naught is R naught over R sub E. If you recall, R naught is the closest the train gets to the core of the Earth. That's R naught. So we have eta naught associated to that, and we have eta associated to any given point. Okay, and so I'm going to also call the surface potential energy V sub S. Actually, you know what? V sub S is the surface potential energy negative Gn me. So that's the potential energy, not the potential. So maybe I'll put this term here. So these V's are a little bit different than the V's we wrote here. Here the V's are potential energies. Here the V's are potentials. So I hope that doesn't confuse you too much. So this is the surface potential energy. This little m is tucked back in, which is the mass of the train or the rider, what have you. So that's the surface potential energy. It's not very important. You can set m equals 1 if you like. So I'm going to set the particle starts from rest. So we have E equals T plus V. So this kind of V. And that's also going to be 0 plus Vs because it starts from rest. And so that's the total energy. So we know the total energy. And at any given time, the energy of the particle is given by T plus V. So this enables us to find the potential at any given point on the surface in terms of the other quantities. So if you look at this expression here, we need to find out what E minus V naught is and what E minus V is. We can use this equation. So first of all, I'm going to write this boxed equation in terms of eta. So V of eta, it's going to be this V with the marks is what's happening here. So I have GMEM over 2RE. So that's going to be my Vs. So it's Vs, but there's this 2. So it's Vs divided by 2 times 3 minus eta squared. So that's our potential at the inside. Now the reason for the 3 minus is because I've taken a minus sign outside. I've taken a minus sign outside because V sub s is negative. Okay, so that's the reason for the 3 minus eta squared rather than negative 3 plus eta squared. All right, so that is your potential at the surface. So this gives me V minus E minus V is what I need for the denominator. So E minus, first let me do E minus V naught. E minus V naught is just going to be V sub s, because E is the total potential of the surface, minus V naught. And V naught is this expression, except at eta naught. So this expression is V naught is V at eta naught. So let me substitute for that. So this gives me Vs minus Vs over 2, 3 minus eta naught squared. All right. I have a Vs and I have a 3/2 Vs. When I take the difference, it's just half. So I get Vs divided by 2, eta naught squared minus 1. You observe that eta naught squared comes first because minus over minus is plus. All right. And then E minus V, by the same token, without the naught, it'll just be the same thing, except you'll replace it, the eta naught by eta. So at last, we're able to write this equation. Pretty complicated stuff, and I don't deny that. Let's see. I want to keep this visible. So let me do that. So I have, I'm going to divide by the radius of the Earth squared. So that becomes eta prime squared plus eta squared is equal to E minus V naught, which is V sub s by 2, eta naught squared minus 1, divided by E minus V, which is Vs over 2, eta squared minus 1. Now I have divided the left side by the radius of the Earth squared. The right side also has to be divided by the radius of the Earth squared. But the numerator has got r to the 4. So I'm going to divide the numerator by the radius of the Earth to the power 4 and the denominator by radius of the Earth to the power squared. If you divide the numerator by r to the power 4 and the denominator by r squared, you're going to end up getting an extra 1 over r squared in the denominator. But that's exactly what you need to produce the eta effect to the left. So everything looks great. Eta to the 4 over eta naught squared. So that's our tremendous simplification, and you notice that details of the Earth simply go away. Now I have to solve this for eta prime. All right, eta prime squared. So let me do that. Eta prime squared is equal to eta naught squared minus 1 over eta squared minus 1, eta to the 4 over eta naught squared minus eta squared. So I have to take the common denominator. Let me do that. So this is just busy work. All right, then the numerator becomes, I'll write everything out. Eta naught squared, eta to the 4 minus eta to the 4 minus eta to the 4 eta naught squared plus eta squared eta naught squared. That's what I get from the numerator. The denominator is just eta naught squared times eta squared minus 1. Mercifully, I get some cancellation. So I get eta prime squared is equal to, there's an eta squared that's common, so I'll take that common. Eta squared has got a negative sign, but I'm going to switch the negative sign here. So this will be 1 minus eta squared. So I'm doing that next. So I'll write this right now and then do that. So once again, if you've been blinded by the quick work, it should be negative eta to the 4 plus eta squared, eta naught squared. I've taken a negative sign outside from both the numerator and the denominator. So this becomes positive eta to the 4 minus eta squared, eta naught squared. And this becomes 1 minus eta squared. So that's our equation. And now we can substitute this back in our original integral. So I don't even think I can find it. Oh, there it is. So here's our original integral. So if I put this back here, so I will divide both sides by radius of the Earth squared first to get everything in eta form, and then we'll see what we get. So going back to that original integral, we have t equals integral from 1 to 2 dt, and that is the integral from 1 to 2 the square root of r prime squared plus r squared d theta over the square root of 2 over m e minus v. I copied it again, so I don't have to keep this. All right. So I want to point out that the Euler-Lagrange procedure has given us the answer, but now we want to find the time. This answer is peculiar. It's just given us the derivative squared of the of essentially the, has not given us the path. It's given us the derivative of the path in a normalized sense, because it's the derivative of the path over the radius of the Earth. So that we can put it back in here to find the actual minimal time. To find the actual minimum time, you have to solve this integral. So that's going to be our next step, because one of the key things in this problem is to find how close you get to the Earth's curve, that's eta naught. Find the time of transit, that's what we are doing now. And the properties of the hypocycloid, I'll talk about soon. So it's still a long way to go in this problem. All right, so divide by the radius of the Earth. numerator and denominator. So I'm going to get integral 1 to 2 square root of eta prime squared plus eta naught, eta squared, not eta naught, over the square root of this 2 over m e minus v. Well, e minus v was here, vs over 2 eta squared minus 1. So I'm going to do that. Because of the vs over 2 and 2 over m, the 2 cancels out. So I'm just going to get vs over m times eta squared minus 1. And then I have d theta. Now, what I'll do here is the following. I've divided by the radius of the Earth to get that. So I have an additional radius of the Earth in the numerator. So I'll just keep that there. Now I'm going to write d theta in a peculiar way. I'm going to write this as d theta by dr times dr. There's nothing that keeps me from doing that. I can always do that. And just to make sure I get my eta factors, I'm going to write this as that. So nothing illegal. I can cancel the drs, I can cancel the r sub e, and get d theta equals d theta. So that's just my peculiar way of writing d theta. So the time t is the integral from 1 to 2, the root eta prime squared plus eta squared over the square root of v sub s over m eta squared minus 1. And then d theta by dr is just 1 over dr by d theta. So that's 1 over eta prime. And then dr over r is just d eta. And this eta prime I got by taking that additional factor of r sub e and sticking it down there. So there's a lot of things that happened here. So each time I have a r, I divide by r sub e, and that brings out the additional r sub e factor up, but I already have one there, and that's what I used to get this thing here. So that's d eta times so that was here. This is what I got here. So I'll just I mean, there's not a continuation of that. That's what I have here. So let me write this. This is d eta over 1 over eta prime. All right, so that's a complicated looking object. Meanwhile, I have eta prime, which is over here, eta prime squared. So let me write that. The time t is equal to the integral from 1 to 2. The square root of vs over m is without the negative sign, so it can be taken out. All right. So let me do that next. All right. Now, negative v sub s is going to be gn me m over re. So let me write that here. Negative v sub s is gn me little m over re. I'm done with that. If I want to take negative v sub s outside, I'll have to interchange the order of 1 and eta squared. Now you have v sub s over m. So let's find out what that is. Negative v sub s over m is gn me over re. Now that's a special term that students of physics will be able to recognize. If you have a person of mass m standing on the Earth's surface, then I can use Newton's law of gravity and say the force of gravity is going to be mass times the gravity on the surface, gs. But Newton's law of gravity also says that's equal to g sub n times mass of the Earth times mass of the person divided by the square of the Earth's radius, because the person in standing at the surface is actually standing at a distance r sub e from the center of the Earth. Canceling m's, I end up getting g sub n me over re squared equals g sub s. So that is a classic way of determining the Earth's mass. You swing a pendulum, measure the acceleration due to gravity, and use this equation, assuming you know the Earth's radius, you can find the Earth's mass. This experiment was done in ancient times. By ancient, I mean Newton's time. And that was how the Earth was weighed for the first time. Pretty impressive days. Here we have g sub n me over r sub e. Well, that is just equal to g sub s times r sub e, because g sub s has got an additional factor of r sub e in the denominator. So we have all that. Let us substitute. Now, there's an r sub e here, and when I carry out these shenanigans, there's another r sub e, so there's an r sub e squared outside. That r sub e squared that is outside will cancel out one of the r sub e's when I bring the v. There's one r sub e left, not two, because one of the r sub e's is already used up in this. There's one r sub e here, but I've taken that r sub e downstairs to form this eta. So this is equal. So there's only one r sub e left. That r sub e that's left is here. But then I have a g sub s times r sub e under the square root sign, because v sub s is under the square root sign. So the upshot is 1 over the square root of negative v sub s over m, which is equal to 1 over the square root of g sub s re, is now going to combine with this re in the numerator to produce a very famous quantity known as the length of the pendulum, LP, which is the square root, length of the period of the pendulum, TP, is going to be 2 pi root the radius of the Earth over g. So this is the period of the pendulum, whose period is equal of a pendulum as big as the Earth's radius in a constant gravitational field that's equal to the Earth's surface gravity. That's called TP. Okay, so I'm getting this square root. I'll be soon getting square root of r sub e over g sub s over there, and I can introduce this t sub p factor. So our calculation is rapidly assuming its final form. So let's put everything together that we have. I'm going to get 1 over root g sub s r sub e times r sub e. And then over here, for eta prime, I've put this. I'm going to interchange the order of eta naught squared and eta squared, and I interchange the order of eta squared and 1. Let me just do that. Actually, excuse me, I should have put 8. I'm going to just do eta prime squared plus eta squared, which is this one, not this one. So I looked at the wrong place. So that's eta naught squared minus 1 divided by eta squared minus 1 times eta to the 4 over eta naught to the power squared. And then here, as I told you before, when I take out the negative v sub s, 1 and eta squared gets transposed. So that's going to give me 1 minus eta squared. And then I have 1 over eta d eta, eta prime d eta. So that's our scary looking integral. It's not that bad, actually. So let me go down. The period t is one of the RE cancels out, so I get square root of RE over G sub S, integral 1 to 2. And then that's going to be the square root of eta naught squared minus 1. And here I'll interchange the order of eta naught squared and 1. So I'm going to get 1 minus eta naught squared, because I know eta naught is less than or equal to 1. So here also I'll interchange the order. So, but here, if I interchange the order, I'm going to get 1 minus eta squared square root, which combines with 1 minus eta squared square root to give me just 1 minus eta squared without the square root. And then I'm just left with eta to the 4 over eta naught squared under the square root. So that becomes eta squared over eta naught when it's taken out of the square root. Lastly, I have 1 over eta prime d eta. Now, eta prime, that's where I'll use this. So this tells me that 1 over eta prime, let's just do this, is going to be the numerator and denominator interchanged and the square root taken. That's why I needed this also. So that, let me substitute for that. Over 1 over eta prime is being substituted for next. So that gives me eta naught over eta times the square root of 1 minus eta squared over square root of eta squared minus eta naught squared d eta. So let's see, are there any cancellations? There's 1 eta that cancels, an eta naught that cancels. So I have an eta d eta. Oh, there's a square root of 1 minus eta squared and a plane 1 minus eta squared. So that will also produce a cancellation. So I'm going to get, this is a constant. So that's just 1 minus eta naught squared times square root of r sub e over g sub s times the integral from 1 to 2 eta d eta over root 1 minus eta squared root eta squared minus eta naught squared. Beautiful. This integral is actually pretty elementary. Now, the integral from 1 to 2 is actually double the integral from 1 to the center point because of symmetry. It is very obvious that this tunnel is symmetric between New York City and Los Angeles. So the point where you have the closest distance happen, which is r naught, that's eta equals 1, and this corresponds to eta naught. So we're going to integrate from eta naught to 1 because the eta is the integration. Eta naught is this distance and 1, and then we're going to double it. So we're going to get a factor of 2 next. 2 times the square root from 1 minus eta naught squared, the square root of r sub e over g sub s, integral from eta naught to 1, eta d eta divided by root 1 minus eta squared root eta squared minus eta naught squared. So this integral is actually what is called an elementary integral. It looks like an elliptic integral. It's not. It's pretty elementary. If you did not have the eta in the numerator, it would be elliptic. But because of the eta in the numerator, a simple u substitution should do the trick. So we'll actually solve it with a couple of substitutions, 2 substitutions, one after the other. So that's our integral we need to solve. So substitution number 1. We're going to set u equals eta squared minus eta naught squared. All right. Then 2 eta d eta will be du, and the limits when eta equals eta naught, the lower limit is going to be 0, and the upper limit when is going to be 1 minus eta naught squared. Okay, I'll call this u1 and u2, the lower limit and the upper limit. So our time integral t under these conditions becomes square root of r sub e over gs square root of 1 minus eta naught squared. I've used up the 2 because 2 eta d eta is du. Integral from 0 to 1 minus eta naught squared du over root u, because that's root u. And this one, 1 minus eta squared, becomes, so eta squared is, by this, eta squared equals u plus eta naught squared. So when I do 1 minus eta squared, I'm going to get 1 minus u minus eta naught squared. All right, so let me put that in there. So I've written this term first, and then I'm writing that term next. So 1 minus eta naught squared minus u. So this is not a bad integral to have, because this integral is not too difficult. It's a trigonometric substitution. So we'll do substitution number 2 next. And that is, I'm going to set some other quantity v equals, actually, let's set u equals 1 minus eta naught squared times sine squared beta. You'll soon see why this is a good choice. Then du will be 1 minus eta naught squared, since that's just a constant. When I take the derivative here, I get 2 sine beta cosine beta d beta. I'm not going to bother changing the limits because that's too stressful. I'll just keep it. Okay, so let me continue with this. The time integral t under these substitutions is the square root r sub e over g sub s, square root of 1 minus eta naught squared. Now I'll keep u equals 0 to u equals 1 minus eta naught squared because I don't want to mess with the limits. Du is 1 minus eta naught squared, 2 sine beta cosine beta d beta over square root of u, which is going to be the square root of 1 minus eta naught squared sine beta, times this thing. So that's set up for that, because when I put u equals this quantity, I'm going to get this comes out. So I'll get the square root of 1 minus eta naught squared coming out. And then I'll get 1 minus sine squared. 1 minus sine squared is just cosine squared. And I put that under the square root, so it becomes just cosine beta. So this is designed so that there's no beta left at the end. So this is pretty beautiful. And if you notice, the 1 minus eta squared also cancel out with the numerator. So even that go away. So that's just integral of d beta with a factor of 2. So it's just amazing that we got to this point with 2 simple substitutions. That's integral u equals 0 to u equals 1 minus eta naught squared 2d beta. Well, that's just 2 times beta, and beta is just arc sine the square root of u over the square root of 1 minus eta naught squared. So that's our answer. The 2 comes over here, so I get 2 root re over g sub s square root of 1 minus eta naught squared d beta, which integrates to beta, which is that. So sine inverse root u over root 1 minus eta naught squared. Between the limits, u equals 0 and u equals 1 minus eta naught squared. So at long last, we are there. This was a long integral, but all the integral steps were fairly elementary. So this gives me 2 root re over g sub s root 1 minus eta naught squared, upper limit. When I put u equals 1 minus eta naught squared, that cancels with that, so I'm simply going to get sine inverse 1. And when u equals 0, that's just 0. So that's just pi over 2, because sine inverse 1 is pi over 2. So at the end of the day, we are getting an integral that looks fairly decent, having factors like pi. So the transit time through the gravity tunnel is now finally determined. That's pi over 2 times 2, so that's just pi times the square root of r sub e over g sub s, and the square root of 1 minus eta naught squared, which is just r naught squared over re squared. Let me take r sub e inside, just to give it a neat appearance. So that gives me pi square root of re squared minus r naught squared over g sub s times r sub e. Okay, now there's an important check that we have to do. You may have actually studied this problem in elementary classes. If you dig a tunnel directly through the Earth, then to the Earth's center, then you're going to have the particle. So suppose you make a tunnel like this, and you drop a particle or drop yourself. Then you're going to shuttle back and forth. The period required for that is the same as the period required for something to orbit the Earth at the Earth's ground level. Now that's never going to happen, because who's going to orbit the Earth at ground level? But that period turns out to be 84 minutes. And that's the same as the period of simple harmonic oscillation through a tunnel. So we have to get 84 minutes if you do this calculation. So let's try to find out what that period would be. So I'm saying that pi times 2 pi times root re over gs is 84 minutes. Let's see if we get half of that, because that's the transit time. So transit time should be pi times root r sub e over gs. That's 42 minutes. And that's one-way travel from the North Pole to the South Pole. When r naught is 0, I get exactly that, because r sub e squared over r sub e is just r sub e. So I get the one-way transit from north to south. Okay, that is north to south plus south to north, one full oscillation. That's just north to south. So we recover that important result in undergraduate physics. So this is our answer. And we have to now figure out the actual specifics of the values. Now let's dwell a little bit on the shape of the tunnel. The shape of the tunnel turns out to be a hypocycloid. And I'm not going to prove this. The video will become way too long if I prove that. So I'll leave it for the interested student. The hypocycloid's parametric equations are as follows. Eta x is half 1 plus eta naught cosine theta plus 1 minus eta naught cosine zeta theta. I'll tell you what zeta is. And eta y is 1/2 1 plus eta naught sine theta minus 1 minus eta naught sine zeta theta, where zeta is a ratio of 1 plus eta naught to 1 minus eta naught. So you can show that this hypocycloid where eta x is x of theta over r sub e, and eta y is y sub theta over r sub e, satisfies the differential equation we produced from Euler's equation, and that is this differential equation. You can show that this is satisfied. It's a long exercise, probably takes another hour to do it, so I won't bother doing it. I will instead do something cooler. I'll construct the hypocycloid. The hypocycloid is constructed by rolling a wheel of radius 1/2 r minus r naught inside the Earth. So that is the construction, and now I would like to spend some time with this construction. I have taken the trouble to create the interior of the Earth. So I'll try to maintain some silence because this requires absolute concentration. I need to roll this without slipping on the inner rim. Oh no, sorry, it was the wrong. I didn't even grab it. Let's try it now. So I'm going to move this out of the way. Let me try another one. Let me try one with red. The curves are looking very strange to me. It's not what I got when I did a trial run. Let me try with this. Try green. Let's try green. See, I'm letting it go. Should not let it go. Okay, this is the best so far, and I'm going to stick with this. Right. Take it to the bank and run, as they say. So that is New York City, and that is Los Angeles. And that is your curve, hypocycloid. Okay, that's the construction we have. The locus of a point on the small circle going over a big circle. Now for the transit time. What we can do is we can use these equations for the hypocycloid to find the transit time, because we need a formula for eta naught squared. The transit time involves eta naught squared. So let's try to figure that out. So this is the final calculation in this video. Shouldn't take us more than 10 or 15 minutes. The transit time had better be less than 42 minutes because that's the transit time to go through the center of the Earth. Okay, so eta naught squared will be eta x squared plus eta y naught squared. So when I say eta x naught and y naught, I'm going to talk about the angle theta at that naught position, at the position where it's, so let me draw another figure. 0.1 and 2. The minimum point, which is this point here, will make a certain angle with the polar coordinate system. I'm calling that angle theta naught. Actually, you know what? Let me take the origin of the coordinate system so that it passes through Los Angeles. So this will be theta naught. In other words, it's exactly half the angle that you're going through. So this becomes, because I'm squaring, 1/4, and then sine squared plus cosine squared is 1, and the cross terms will cancel out because of the minus sign. So I'm just going to get two terms, 1 plus eta naught times cosine theta cosine theta squared. I better do this carefully. This first term is 1/4, 1 plus eta naught squared, that squared, cosine squared theta, plus 1 minus eta naught squared, cosine squared zeta, theta naught. That naught means theta naught. So that's eta x squared plus eta y squared. Oops, then there's a plus 2 cosine, 2 times 1 plus eta naught, 1 minus eta naught, cosine theta, cosine zeta theta. And then the other one gives me 1 plus eta naught squared sine squared theta plus 1 minus eta naught squared sine squared zeta theta. There's no cancellation because of the different looks. 2 times 1 plus eta naught, 1 minus eta naught, and then I get sine theta sine zeta theta. So when I add these two terms, cosine squared plus sine squared is 1, cosine squared zeta theta naught plus sine squared zeta theta naught is also 1, and this cosine theta naught cosine zeta theta naught plus minus sine theta naught sine zeta theta naught is just cosine a plus b, because if you recall, cosine a plus b is cos a cos b minus sine a sine b. So I have to use that. Okay, so combining all these terms, I get eta naught squared equals 1/4 1 plus eta naught squared plus 1 minus eta naught squared plus 2 1 minus eta naught squared, because a plus b times a minus b is a squared minus b squared, so I get that, times cosine of this plus that, so theta naught plus zeta theta is zeta plus 1 theta naught. Okay, so now we have to find out what zeta plus 1 is. Zeta is this. So zeta plus 1 is 1 plus eta naught over 1 minus eta naught plus 1, which is going to be, take the common denominator. So I get 2 over 1 minus eta naught. Okay, finally, what have we got? So 1 plus eta naught squared plus 1 minus eta naught squared, if you expand this out, that's just going to be there's a minus 2 eta naught term that cancels out with the plus 2 eta naught term. So you're going to get a simpler equation. Let me write it out. Eta naught squared equals 1/4 1 plus 2 eta naught plus eta naught squared plus 1 minus 2 eta naught plus eta naught squared. So that gets rid of our term there. plus 2 times 1 minus eta naught squared cosine 2 theta naught over 1 minus eta naught. So there's a half, there's a 2 there, there's a 2 there, there's 2 here, and there's a quarter there, so that becomes a half. Half 1 plus eta naught squared plus 1 minus eta naught squared cosine 2 theta naught over 1 minus eta naught. So at last we have an equation that we can work with. Unfortunately, it's what's called a transcendental equation, which means the left-hand side has got eta naught squared and the right-hand side has got eta naught buried in cosine theta. So at this point, a computer is the only option. And indeed, I took the opportunity of putting this in Wolfram Alpha. But fortunately for us, I just realized when I did all that, I realized, oh, I didn't have to do that at all because the answer was so simple. So I realized that that did not have to be done at all. It's a fake transcendental equation. I'll tell you why. So this is eta naught squared equals 1 plus eta naught squared over 2 plus 1 minus eta naught squared over 2. I'm taking the 2 inside times cosine of 2 theta naught over 1 minus eta naught. Now, if you cancel out, I'll get eta naught squared over 2 on this side, and then I'll bring the half on this side, minus half, which is eta naught squared minus 1 over 2, and that's equal to 1 minus eta naught squared over 2 times cosine 2 theta naught over 1 minus eta naught. Observe this. The left-hand side is the same as right-hand side multiplied by cosine, except there's this interchange. So that tells you that cosine of 2 theta naught over 1 minus eta naught must be equal to minus 1, because only if you have that to be equal to minus 1 will it flip the sign and give you the left-hand side. So it's as beautiful as that. Minus 1 is also known as cosine of 180 degrees. So we can actually solve this equation quite simply. 2 theta naught over 1 minus eta naught is just equal to pi, which means that 2 theta naught over pi must be 1 minus eta naught, and eta naught, therefore, must be 1 minus 2 theta naught over pi. Now, theta naught is half the distance, angular distance between New York City and Los Angeles. So so 2 theta naught, which is the complete angular distance, is just going to be the arc length S between New York City and Los Angeles divided by the radius. So this tells me that eta naught must be equal to 1 minus the arc length S over pi times r sub e. Now it's just a question of looking things up on Wikipedia. So from Wikipedia, and here again, it's an act of faith, because who can believe anything in Wikipedia these days? But I'm hoping that some things are true. So according to Wikipedia, the geodesic distance between Los Angeles and New York City, S, is 4,139 kilometers. And according to some other facts, the distance between the Earth, the circumference of the Earth, excuse me, is 40,075 kilometers. So I took the liberty of putting all this in, and I got eta naught to be 0.6295, which means that it comes 63% close to the Earth's center. Not a bad calculation at all. So the transit time, t transit, which is going to be the square root, where was that thing there? It's given by that. Now this can be written as pi times the square root of r sub e over g sub s times square root of 1 minus eta naught squared. So I'm going to go back to the old way of writing it. Well, this I already know. That's 42 minutes. So this is 42 minutes times the square root of 1 minus eta naught squared. So if you work that out with eta naught equal to that, you're going to get 25.56 minutes. Pretty impressive. You get to New York City, from New York City to Los Angeles in less than half an hour. Now, of course, you have to take some obvious precautions. If you calculate the speed of the particle at the center of the Earth, it'll turn out to be something like 8 kilometers per second, which is approximately 24 times the speed of sound. Here, because it's not quite through the center of the Earth, it's not going to be quite Mach 24, but it'll still be something like Mach 15, let's say, 15 times the speed of sound. So you absolutely have to remove all the air in the tunnel, which is also a good thing to do, because if air resistance is there, the gravity train won't reach completely. It'll be stuck somewhere 100 kilometers from Los Angeles inside a dark tunnel, and you don't like that. You want it to go all the way. There are obviously other factors to consider, because the Earth is not a sphere, it's a geoid. So if you start from New York City, it may actually not make it all the way to Los Angeles, even if conditions are perfect, because the curvature of the geoid shape of the Earth is more pronounced at Los Angeles than it is in New York City. Conversely, if you start the train at Los Angeles, it may shoot out of the air into the air in New York City because of the geoid flatness. So these are all the precautions you have to take when you actually build this tunnel, if you bother building it.